So you say on this boundary, either wave function is continuous or the space derivative of that wave function is continuous. But you don't call them Dirichlet or Neumann. Their names are actually those names. In thermodynamics, you do the same thing. Clear? So your geometry is actually defining those boundary conditions. What we do in electrodynamics, we say on a given boundary, potential will be fixed. Fixed means defined there. Its value will be given. Or the space derivative of the potential. So the space derivative of the potential is electric field. So electric field will be given. But here we say that this electric field will be very special one. It will be normal to the surface, which we call the normal derivative as well. So the first boundary condition, Dirichlet boundary condition, potential will be fixed there on a boundary. Second boundary condition, electric field will be fixed there and potential will be free. You are not supposed to fix both conditions, right? You are not supposed to fix both conditions, otherwise it will cause inconsistencies. Means they are interrelated. Okay? For example, if you ask me to go on one foot, then I can do that. Okay? Like I raise one leg and I can go. But if you say raise the other one as well, then I can't do this thing. So at the same time, you will have to fix one condition only. Then it will give you the solution. If you fix both, then it's not possible. Like I fix both of my legs and I want to walk. It's not possible. Clear? So, the very first boundary condition. Okay, this thing will remain there, so we will come back here whenever you get lost that what we are doing. So I will come here and will interpret this thing. The very first thing that, let's see that what this is giving you, del square phi is equal to 0. You know phi is a function of x, and here x is three-dimensional like phi of r. So I can write that in one dimension. If I want to write this thing, this is d square phi over dx square is equal to 0. If I integrate both sides, then I will get d over dx of phi is equal to a constant, and that is c. And then another integration, or let me write this thing as m constant. Another integration will cause this thing phi of x equals mx plus another constant, mx plus c. So in one dimension, if I solve this equation in Cartesian coordinates, then it gave me the equation of a straight line, which is having almost no information in it. But if you will solve this equation in 3 dimensions, we will have a lot of information, and we will do this in, after covering the next chapter. When we will go to the 3rd chapter, we will solve this equation in 3 dimensions in spherical polar coordinates. You have already done the same thing in basic electrodynamics, but basic electrodynamics are the electrodynamics by Griffiths. That is not a good chapter, because over there everything is coming automatically. There is no derivation behind. Just a little bit of logic, and then solution is written directly there, because it is out of, you can say, your approach. While in the Griffiths quantum mechanics, it has been solved. You know the solution of the Schrödinger wave equation in spherical polar coordinates. You have the solution of the azimuthal component. You are having then the radial and the azimuthal components, right? You are having the zenith angle component and the radial component. Some of them are giving you the Legendre polynomials. Then those Legendre polynomials are then associated Legendre polynomials, and then they end up in spherical harmonics. So they are all, you can say, the solution. It is very hard to solve it directly, so you are solving it in pieces with the help of separation of variables. And you are seeing little bit things over there. The radial component giving you the principal quantum number, and then the orbital giving you some other quantum numbers and spin quantum numbers, and they go on. So that you have already done in Griffith's quantum mechanics. Over here, we will actually solve this thing from the point of view, because this is the second order differential equation, the Laplace equation. We will solve this according to electrodynamics requirements, and we will also see some features of this thing. Okay, so the straight line equation, it is not giving lots of informations. We will do this in the third chapter, but first we define the boundary conditions and the uniqueness of this. Let's say the very first boundary condition, which is Dirichlet boundary condition. And in Dirichlet boundary condition, I will write BC. In Dirichlet boundary condition, you will have to specify phi on boundary. Means you will specify potential on a boundary. And this one is after Dirichlet. Dirichlet was a German scientist, mathematician, Johann Dirichlet, which is Johann Dirichlet. And at the same time, you will have to suppose curly phi by curly n prime is free. This one you are not restricted. Like potential you have fixed, while the electric field is free. When we will fix electric field, potential will be free. Okay. Now, let's say that when we will solve for phi, and we will claim that the solution is unique, then how we can prove this thing? Let's assume that there are two solutions. One solution is phi 1 and the other solution is phi 2. Then if this is del square phi 1, it will be equal to 4 pi k rho. 4 pi k rho. And if it will be del square phi 2, it will be minus 4 pi k rho as well. Because the Poisson equation will remain the same, phi 1 and phi 2. So I can write that as they are both equal, so del square phi 1 minus phi 2 is equal to 0. Because they are equal. Now let me define u such that this is equal to phi 1 minus phi 2. Then I can write that del square u will be equal to 0. So this del square u will be equal to 0 inside the volume. Inside which volume? Inside that volume in which I am doing this, I am calculating it. So, but what about when del square u is equal to 0, then on the boundary I will have u equal to 0 on the boundary. right? When del square u is equal to 0 inside the volume, like you say that u is your potential, and the Laplace equation is telling you that you are not enclosing any charge. So del square u will be equal to 0 as you are having del square phi equal to 0. So it is inside that volume in which you are calculating it. What will be the situation on the boundary? On the boundary, u is equal to 0. So when u is equal to 0, means that we will have to solve for u, right? We will have to solve for u. Okay, I will write and u equal to 0 on the boundary. So the Green's first identity is that phi is equal to psi is equal to u. Then I can write that integral on a whole volume del u dot del u plus u del square u and d cube x is equal to on a surface and u curly u over curly n and dA. This is the surface, this is the boundary. Now I say that on the boundary, on the surface, u is equal to 0. So this term goes to 0. And similarly, here this one will go to 0. So I can write that integral on volume del u mod square d cube x is equal to 0. Means gradient of u is equal to 0. What does it mean? The space derivative of u is a potential, right, is equal to 0. When a space derivative is equal to 0, when u is 0 by itself, right, its derivative will be 0. Or when u is something fixed, is something constant, then space derivative will be equal to 0. So it is having some fixed value, and that value is 1 only. That value is unique only. That value is single. And this implies that u is equal to 0 everywhere. And u equal to 0 means that phi 1 is equal to phi 2. Means the region in which you were expecting that there will be two solutions for the potential, those two solutions are actually the same. So it is a unique solution. Now this equation is telling you that your mathematics is very exact, is very clear. It will give you a solution and there is no possibility you are having another solution, right? By the way, when you are having a second order differential equation, how many solutions you have? Two. And here you will have one solution. Why? Because one solution is in the form of a boundary condition, right? One solution is in the form of boundary condition, and one solution you will get which will be a unique one. Clear? By rules, second order differential equation will have two solutions. Okay, and now with the same logic, we can write the Neumann boundary condition as well. Neumann boundary condition. So what we do in the Neumann boundary condition, we specify electric field on a boundary. We specify curly phi over curly n on the boundary. So now when you fix the value of electric field on a boundary, then your potential, your pi will be equal to free. You cannot restrict that one. And the solution can again be shown by analogous reasons, and again taking u equal phi 1 minus phi 2, and within the surface, we will have del square u equals to 0 and curly u over curly n will be equal to 0 as well, and this will imply, again, means you use the Green's function again. So now this thing is equal to 0. Similarly, this thing will be equal to 0. So again you are having del square u gradient of u squared d cube x on volume is equal to 0, and you are again having u equal to 0 everywhere, and this says that u equal to 0 everywhere, and u equal to 0 everywhere means phi 1 will be equal to phi 2. There is one thing which I will say a bit more, and you will see this thing. Okay, we will do calculate one thing more, like in the Green's function, sum of this term and this term, we have made this one equal to 0, then sum of the term is remaining there from averaging that value, and that we will discuss after a while. But first we say solution of Poisson's equation using Green's function. Solution of Poisson's equation using Green's function. Right, Green function, using Green function. Okay. We know that potential of a point charge is a very special situation, because the potential of a point charge, the potential of a point charge is equal to 1x minus x prime. So this is rather a special function, and this requires no boundaries because it only requires the charge distribution. We have written it here that this only requires a charge distribution, and this thing is equal to a delta function. Is I can write that del square
1 over x minus x prime is equal to minus 4 pi delta x minus x prime.